Here we have part of the graph of the function f of x equals x squared plus 4x minus 12 over x squared minus 2x. Now, the function is indeterminate at x equals 2. That's because if we try to get f of 2, well, in the denominator we get 2 squared minus 2 times 2. That's 4 minus 4, which is 0. In the numerator we get 2 squared is 4 plus 4 times 2 is 8. 4 plus 8 is 12 minus 12 is 0. So we get 0 divided by 0, and that can equal any number we like. We could set it equal to 7, for example, because if we multiply 7 by 0 we get 0. Or we could set it to equal minus 3, because minus 3 by 0 is 0. So at x equals 2 the function is indeterminate, so we just ignore the function at x equals 2, so we just have this circle here. So this point is removed from the graph. Notice though, as we approached x equals 2 from the right, that the function is approaching 4. Here we have a table of values showing values of x that are greater than 2, but those values of x are approaching 2 from the right. So we start off at 2.5, f of x is 3.4, and as we run down through these values, as we get closer and closer to 2 from the right, we can see that f of x appears to be approaching 4, and you can see that clearly on the graph. Notice also that as x approaches 2 from the left, then f of x approaches 4 from above. So here are some values tabulated. Here we have values of x that are less than 2, and as x approaches 2 from the left, as we get closer and closer to 2, we can see that these values appear to be getting closer and closer to 4. Notice again that we are not interested in x equals 2. We're only interested in values of x that are approaching 2, either from the left or from the right. To summarize this table, we say that the limit as x approaches 2 from either end, from the left or the right, of our function x squared plus 4x minus 12 divided by x squared minus 2x is 4. Now let's look at this function g of x, very similar to f of x. Actually, g of x is the same as f of x for values of x that are not equal to 2. However, this function is defined at x equals 2. At x equals 2, g of 2 is 6. This is a function. For each value of x, we have a unique value of g of x. So at x equals 2, we just have one value, and that is 6. If I draw a vertical line from 2, it will cross the graph at just this one point. We just have a gap here. Again, if we take the limit, not of this thing, but well, we can call this g of x. If we take the limit as x tends towards 2 of g of x, we get 4. We don't get 6. That's an important point. So when we say the limit as x tends towards 2, we are saying that x is not equal to 2. So again, it doesn't matter which way we approach 2. If we approach 2 from the left, g of x is approaching 4. It's not approaching 6. If we approach 2 from the right, g of x is approaching 4 from above. G of x is not approaching 6. Let's look at a function f of theta equals 1 minus cos of theta all divided by theta. Theta is in radians, and we want to consider the limit as theta tends towards 0 of f of theta. Now, if we calculate f of 0, we get 1 minus cos of 0. Well, the cos of 0 is 1 divided by 0. That's 0 divided by 0. And as we saw before, this is indeterminate. We can set it equal to anything we like. We could set it equal to minus 9.3, for example, because minus 9.3 multiplied by 0 gives us 0. So the function doesn't even exist at theta equals 0. However, when we take the limit as theta tends towards 0, theta is not equal to 0. Theta is approaching 0 but never reaches 0. And we are interested in seeing what f of theta approaches. Here we have a table of values for theta. Now, on this side of the table, the values are positive. These are values that are greater than 0, so we are approaching 0 from the right, starting off at theta equals 1. And as you can see that as we approach 0 from the right, we go from theta equals 1, 0.1, 0.0, 1.001. These numbers are actually approaching 0 as well. To see that more clearly, let's take a number that's even closer to 0. Let's say we take 0.00001. So to get f of 0.00001, we have 1 minus the cos of that angle. So the calculator must be in radian mode. So get the answer to that. And then we have to divide by theta. So we have to divide by 0.00001. So this looks like 4.9 recurring by 10 to the power of minus 6. So we have to move the decimal point 6 places to the left. So we end up getting this number here, 0.0000499 recurring. So we can see that this number is even closer to 0. So it appears that the limit as theta tends towards 0 of f of theta equals 0, at least when we approach 0 from the right. Now we need to check what happens as we approach 0 from the left. So here we have a table of values for theta that are less than 0 but are approaching 0, starting with theta equals minus 1. Notice that f of minus 1 is minus f of 1. So to see that, let's just write that out. So we replace theta with minus 1. Now the cos of minus 1 is just the same as the cos of 1. So in general, the cos of minus a is equal to cos of a. But notice here that this is the same as minus 1 minus cos of 1 divided by 1, which is minus f of 1. So f of minus 1 is the same as minus f of 1. So we just have to minus all these values here to get the values of f of theta as theta approaches 0 from the left. And you can see the same thing is happening. These numbers are getting closer and closer to 0, but from the left. So it appears, and indeed it is the case, that this limit is equal to 0. The point is that for this limit to equal 0, f of theta has to approach 0 as theta approaches 0 from both sides, both from the left and from the right. Here we have a graph of the function f of t equals cos pi over t. Again, t is in radians. Here is a table of values of f of t as t approaches 0 from both the right and the left. So notice that as t approaches 0 from the right, f of t, well, at least for these values, 0.1, 0.01, 0.001, is just equal to 1. As a matter of fact, the graph oscillates wildly from minus 1 to plus 1 as t approaches 0 from the right. So as t approaches 0 here. For values of this form, f of t is 1, but for other values we would actually get minus 1. We will even get 0 for other values, but let's take this number here, which is even closer to 0. So we want to take pi and divide by 0.00001. So we want to get f of this number. Then we want to take the cos. So our angle is assumed to be in radians. Notice that we get plus 1. And that is indeed the pattern. No matter how many zeros I have here, if they're followed by a 1, then f of t will equal 1. The same is true if t approaches 0 from the left. Okay, so we start off with a value of t that's less than 0, like minus 1, and calculate f of t. And we can see that numbers of the form minus 0.000 and followed by a 1 gives us 1. That's because if we take the cos of a negative number, say the cos of minus a, well, that's just the same as cos of a. So the cos of minus 0.001 is the same as cos of plus 0.001. So you might think that the limit is 1. because when we approach 0 from either the right or the left, f of t appears to give us the same value of 1. But the problem is, if we take values other than these values here, we can still take values very close to 0 but that are not of this form, and we won't get 1. We are not zooming in on a unique value. If we take this value of t, for example, we actually end up getting that f of t is not 1 but 0.95 to 2 decimal places. As a matter of fact, as we get closer and closer to 0, the graph oscillates more widely from -1 to +1. So we are not settling on a unique value, so this limit does not exist. Finally, let's look at this function, the Heaviside step function. H of t is 0 when t is less than 0. H of t is 1 when t is greater than or equal to 0. So this point is not part of the graph, but 1 is. So, for example, h of 0 is equal to 1. A function has to have a unique value for each value of t. So we can't have h of t equaling both 0 and 1 at the same time. So that's why h of t is 0 for t strictly less than 0. But at 0, h of t is equal to 1. So at 0 we just have a unique value for the function. That's what we want for a single valued function. They're the types of functions that we deal with. By the way, sometimes this function is written u of t, u for unit step function. So we have a step here, and the step occurs at the origin, and it's a step of 1 unit. Anyway, let's consider the limit of h of t as t approaches 0. Well, you can see quite clearly that as t approaches 0 from the left, it appears that the function itself is approaching 0, the graph is approaching 0. But when we approach, when t approaches 0 from the left, I should show it down here, t is approaching 0 from the right, the function is actually approaching a different value. It appears to be approaching 1. So unlike in the previous example, we are approaching a value, but it depends on which side we approach 0 from, whether we approach 0 from the left or whether we approach 0 from the right. If we approach 0 from the left, this limit is equal to 0. But if we approach 0 from the right, this limit is equal to 1. We are not settling on a unique value. So again, we say that this limit does not exist.